It does everything cow, similar to ZFS, copy on write. So all of its I/O transactions take place copy on write, although you can disable that optionally. And also, as a result of the copy on write functionality, you can also take snapshots. So you can do simple cow snapshots a lot like you can with ZFS. Again, like ZFS, one of the most interesting aspects of btrfs is that it supports multiple devices and storage pooling. So right now it just does RAID 0, RAID 1, and it can also do RAID 10. But there are plans in the future to support more levels of redundancy like erasure coding and such. It can also do dynamic rebalancing. So if you dynamically resize your file system, you can rebalance all of the data on it. Although right now that process involves reading and writing, rewriting every object in the file system. So that does take a bit of time and I/O workload, but it can handle that task online. So also it's, it has the concept of cow snapshots, just like ZFS. So you can create mountable read-write snapshots, or you can store read-only snapshots for backup purposes. And it also supports transparent compression, also again like ZFS, using zlib. And I think they have some plans to support additional compression methods in the future. But right now it just does zlib optionally. So looking ahead, they're looking to develop actual erasure coding features, so actual RAID 5, RAID 6, sort of real redundant RAID features. There is no FSCK at this point. So although I wasn't able to knock the file system over during my tests when everything ran correctly, kicking a node while it was performing I/O to the file system toasted my file system since I had no FSCK to recover it. So that's a bit of an issue so far. But this is being developed out of Oracle, whom I trust implicitly to continue development on this very important community file system. So they also want to introduce deduplication, so block, the standard block dedupe that you'll see out of a lot of RAID heads. And they also want to extend the transparent compression layer to do some on-disk encryption, so in case you want to store sensitive data. So obviously this has some interesting implications for use with Lustre, and although Johann will get into that in his portion of the talk, it's worth mentioning that at least the multiple devices could really let us get out from under these really big, expensive, powerful RAID controllers, with apologies to our lug sponsors. I did a few simple tests, and I used, here's just the slides, describing the test platform, right? And as I describe the test platform, I should also, credit Sarparal's information. If you saw his talk yesterday on I/O benchmarking, he really does make a lot of good points, and in fact, it's a much more complicated task than it ever seems like. So I appreciated Sarp's insights at ORNL, and I think his talk was, contained a lot of fine information when you're doing this type of work. So thank you, Sarp. Not something I say very often. I was running with the 2637 version of btrfs, which contains some recent enhancements, including it has a new on-disk free space cache. But still, again, no FSCK. So don't try this file system at home. Although I think Johann actually said he ran it on his laptop, so brave guy. And I just did it with a simple SRP initiator. Oh, that's right. I forgot to mention in my still to come slide that right now btrfs, since it uses and Johann will get into this, but since it uses chunking to do its object storage, it creates large chunks of extents on the different devices that you use. If you fill any of those chunks up, you get eno space. And it's not obvious, unless you want to interrogate the B tree directly, it's not obvious to figure out where your data is stored or how the data is laid out such that you can avoid accidentally filling one of those buckets. So right now, full file system issues are a little gray. And you'll see also that there are still some issues with accounting for exactly how much disk space you have, how much you're using, and how much you can fill up before the file system declares itself full. And I think they're doing some work in that area. Okay, So what I was mainly interested in is figuring out how well btrfs was going to work on multiple devices because, as I said, obviously, with apologies to our sponsors, we want to get out from under these expensive and complicated RAID controllers. And take a look at how much overhead things like the compression layer would add. Now we'll get to all the pretty charts and graphs. Just a baseline that I included raw performance on this slide, and I'll just leave that for the for material in the in the backing slide deck. It looks like my axis label didn't come through here, though. The axes labels are all megabytes per second. So what I did is I tested from using individual disks that I ganged together with Linux, and then disks that I rated together using the Ingenio. So you'll see the results talk about single device and multiple device with btrfs. With the single device, I was using disks that were ganged together using the Ingenio, and the goal being to determine how much better btrfs could do if it had control of its own disks, as opposed to relying on the RAID controller. All right, so getting right into the simplest numbers, looking at sequential write performance, btrfs does seem to outperform ext3fs here. In most cases, it just edges it out slightly. These were bulk write tests with just a straight up AIO write with a deep queue, and so it's possible that btrfs queues up a little better here. What's interesting to note here is that with multiple devices, the sequential I/O performance doesn't really improve all of that much over just using them ganged together, which you would kind of expect, because there's not a whole lot of extra work in managing the disks. So. And read is the same way. You'll see you'll see in a couple of these cases, btrfs seems to roll over a little bit when I get up to using 4 disks. So hopefully that will improve a little bit over time, and especially as enhancements are made to the multiple device code. And you'll see here a case of this here in the sequential read performance. Although on single devices it kept up with the ext3 just fine, which is what you would expect. So the oh, you can't read the legend on the graphs? Oh yeah, it does look a little small. Okay, so yeah, I'd be happy to, Sarp, thanks. Sarp, you forgot to include in your talk about benchmarking I/O to label your graphs clearly, so I didn't do that. The blue bars on the left indicate btrfs on single devices ganged together with the Ingenio. The red bars indicate btrfs in control of its own disks, and the green lines are ext3. And that's the same for all these graphs, I think, except the ones that are a little busier that have multiple bars. So a random workload is really where we'll see something more interesting. Doing a sequential workload on a couple of different file systems just proves that the file system developers weren't entirely nuts. And in terms of random write performance, you'll see here that btrfs does do considerably better when managing the devices itself than it does when they're being managed by the RAID controller. It still doesn't quite catch up to ext3 yet, but I would hope that we'll see some performance improvement there over time. And again, in the ext3 case, the disks are ganged together by the Ingenio, just like they are in the single device case with btrfs. You can also see that the random write performance actually degrades a little on the using btrfs so far as you increase the number of devices. Random reads does much better, and in fact, it manages to keep up with the multiple device case and with the ext3 during in the random read case. So that's good. All right, so using file system benchmarks is fun, and it tells us lots of interesting and mostly meaningful things. To do some, I tried to come up with a couple of more interesting tests, and one of them was just untarring a really large file. Turns out that I just ganged together a few Linux kernels, tarred them up, and decided to see how quickly each of the file systems could handle untarring a really large file. So I took, I think it was 4-ish copies of the Linux kernel. It was about 1.7, 1.8 gigabytes, all zipped up well, I shouldn't say zipped, I should just say tarred up since it was uncompressed. Stored it in memory and timed how long it would take the file systems to decompress those files. Or I said decompress again, to untar those files. And so these, yeah, again, my axis labels didn't come out that great, so I'll explain what's going on here. But these values for the untar test are in seconds, so lower is better. So the tests here are looking at the blue bar is on the left is the btrfs single device case, again with disks ganged together by the Ingenio. The green bar, the third from the left, refers to btrfs in the multi-device case when it's managing the devices itself. And finally, the teal bar on the far right is for ext3. Whoever designed the color schemes for Microsoft Excel's graphing must not have been working with a PowerPoint developer to get good slides here. Now, what was interesting when I was doing this untar is btrfs will store small files right in its B tree as opposed to placing them in disk extents. And there's the couple bars that I haven't explained yet are the timings I got when I rewrote, when I untarred the file over the top of itself. So btrfs apparently has a lot more work to do rearranging the B tree in that case. And you'll see it gains some performance benefit from doing that. And here also, btrfs seems to do slightly better when it has when it manages the devices itself, but again, not far and away blowing away the RAID controller at managing disk drives. And it does edge out ext3 in most of these cases. But I noticed that I happened to notice that the rewrite cases were pathological, and so I thought I would include them in here, you know, for just because I thought they were interesting. All right, so I turned on the transparent compression features to determine, you know, how much overhead they would add to something like this. You know, you'd figure uncompressing source code is going to, you know, result in a pretty good compression ratio, and in fact, it does. I got about 3-to-1 compression on the file system. And the CPU load wasn't terribly bad either. But you'll see here, especially on well, that's right. I need to explain what the heck you are seeing before I can tell you you will see it here. So in doing the same test, I looked at a few different btrfs configurations. So on the left, the blue bar refers to simply running the test uncompressed. It's a duplication of the result on the last slide for comparison purposes. Then on the red bar refers to btrfs again with a single device with the disks ganged together by the Ingenio, and the yellowish bar refers to the multiple device case where btrfs is managing the disks itself. And then the green and teal bars refer to the rewrite case, which again I'm including here just because I thought it was interesting. Now you'll see here that you know, compression actually improves your I/O throughput when you have a highly compressible workload because you're simply doing less work. However, your benefit is capped at the rate at which the client can decompress can compress the data. And in fact, the numbers you see here, just like 85, 90 megabytes a second here that I was getting with btrfs, or 85, 90 seconds, excuse me, that was taking to write the data out with btrfs is about as fast as the host could compress it. And I verified that just by having the host compress it a few times and timing that, and it lands right about there. So you can see the benefit sort of goes away, and I was essentially running with a host that was outrunning its disks in that sense. Okay. And finally, turning on compression, doing random I/O doesn't really seem to it doesn't seem to affect performance too much, but then again, there were very few ones in my I/O workload, so that's also not likely to you know, result in a lot of big changes there. And the write performance case, the random write performance improves greatly using compression when btrfs manages the devices itself. I think that's my last graph, so I'll let Johann, I'll yield the floor to Johann. I think the plan was to take questions at the end, so I'll remain handy if anybody wants to ask me something as well. So, Johann?
So I'm going to start with a quick dive into btrfs internals, and more particularly the disk layout. Then I will present some interesting btrfs feature from the Lustre perspective, and finally I will gather the requirements for the implementation of a btrfs OSD. So btrfs uses B-tree. The B-trees are updated in a copy on write manner. This means that blocks are never overwritten. Each time you want to update a block, we write it to a new location. A btrfs uses reference counting for blocks and nodes inside the B-tree. This means that one block can be shared, can be referenced several times inside the same B-tree, or can even be shared between two different B-trees. If there is one thing to remember about this slide, that's the fact that btrfs stores all file system structures inside the B-tree. This means that all metadata structure, and even to some extent data, if they can fit into a leaf block, are stored inside the B-tree as an item. So one of those items can be looked up through a key. The btrfs key is divided into three parts. The first part is the object ID. So a unique object ID is allocated to every object. So that's typically the inode number. Then for a given inode, you can have multiple metadata structure associated to this inode, typically the inode core, to list all the directory entries, extended attribute, extent. So btrfs uses the type field of the key to identify what kind of metadata structure we want to look up for a given inode. And then even for a given inode and a given metadata structure, you can have multiple instances of this structure. One example is for extent. You have multiple extents per file. So in this case, the last field of the key is used, that's the offset field. So the offset, in this case, in the key, that's the logical start, the logical offset inside the file where the offset, the extent starts. Another example is directory entries. So you have multiple directory entries for a given directory. So we make the tree can look up one specific directory entries thanks to the offset, and in this case the offset is stored to the checksum of the file name. So the object ID is the most significant bits of the disk key. This means that all the B-tree algorithm try to store item sharing the same object ID close together on disk. So this is something that the btrfs B-tree grants. So the way the items, so the metadata structure are packed on disk is very interesting. Unlike all traditional file systems who have one type of metadata structure per block, so usually typically in ext3 you have inode bitmap in a given block, then inodes, the inode table is stored then on one block. btrfs mixed all those metadata structure together inside the same block. So it works that you have a stub at the beginning of the leaf block, which is the item, and tells you an offset and a size. So then it points at the end of the block where you can find the core content, the core of the item. So the end result is that you can have a leaf block with an inode sitting next to an extended attribute of we can have a different size, sitting next to a directory entry and then another inode. So that's very space efficient and very different from traditional file systems. So the directory structure, so btrfs uses two indexes. The first one is for lookup, and the second one is for readdir, to return inodes in inode number order. This is to read inodes sequentially on disk. But btrfs uses a third type of item for directory entries. That's the back reference. So this is general to how btrfs works. Each time there is a reference from a parent object to a child object, there is also a back reference from the child object to the parent object. This is used for many purposes. The first one is when you want to remove a reference, you can check that this reference is valid thanks to the back reference. The other use case is for file system resize. btrfs knows exactly what object and what item is stored at a given offset on disk. So when you want to shrink the file system, btrfs know what object is stored inside the part of the file system that you want to remove, can check how many copies it has, and make another copy if needed. It also simplifies the work of FSCK. We can just check that all the references are valid, take to the back reference. So all this has a cost. The cost is 3 items for one directory entry, and each one of those items stores the file system name. So yeah, the metadata overhead is quite bigger, larger than for ext4, for instance. So btrfs supports multiple devices. The way it works is that it divides all the devices into 1 GB chunks. Then it combines all those chunks together to create a virtual address space. Then this virtual address space is divided into virtual groups. Each virtual group is assigned a type. So this can be system, metadata, or data. And you can have a different RAID configuration for each virtual groups type. Typically RAID 0, 1, and 10, since btrfs does not support yet RAID 5 or RAID 6. So the logical to physical address mapping is handled by a dedicated B tree. So actually, btrfs has multiple B trees. And the chunk tree is a reference from the btrfs superblock, is in charge of translating the logical address into a device ID and a physical address. So here is a quick overview of how the chunk tree operates. At the top, you have the logical address space and 3 virtual groups. The first virtual groups is associated to chunk 1, which is in yellow. So this is typically a metadata virtual group, which will be mirrored across 2 devices, device 1 and device 2. Then you can have 2 other virtual groups, the red one and the green one, which are data virtual groups, and which are RAID 0 configuration. So the chunk tree is in charge of the translation from a logical address to a list of device physical address. So some interesting btrfs feature. I think it is worth mentioning the equivalent of it to scan. So thanks to the copy on write feature, it's very easy to list all recently modified files. We just have to parse the B tree and check. So basically, each time a block is updated, it is returned to a new place, and btrfs update the generation pointer, which is basically the transaction ID. So you can walk the B tree and find all recently modified files by just comparing the generation pointers. So here is one example where I could list all items that have been modified since transaction ID 38,276. So 2 items were modified. So it does not only give you the item, it gives you the items. So items means metadata structure. So in this case, 2 extents were updated. So as said previously, btrfs can store small files, so in a leaf block, if they can fit in a leaf block, typically 4K. And there is a mount option to disable this, or to say I only want to store files smaller than 2K, for instance, in the B tree. btrfs does support checksum, only 1 checksum types as of today, which is CRC32C, but the on-disk layout allows us to support different checksum types in the future. One last interesting feature is the in-place conversion from ext4. There is a tool called btrfs convert, which creates a btrfs file system inside the free space of an ext4 file system. The ext4 file system is available as a snapshot. Basically, the btrfs file system duplicates all the metadata and points to the data block of the ext4 file system. So you can then test how btrfs will perform on your file system. If it was replaced by if you replace btrfs, if you replace the ext4 file system with btrfs, and if you are happy with the result, you can just delete the ext4 snapshot. You will get the space back, and then you are stuck with btrfs forever. Or you can decide to roll back to ext4 by just restoring the ext4 superblock, and then the btrfs file system will be gone, and ext4 will use the free blocks, which were used previously by btrfs. So there are still some shortcomings which need to be addressed if we want to use btrfs as a backend file system for Lustre. The first one is, as it was previously mentioned, there is no FSCK support yet. Actually, the status is that the checker works,